let's go ahead and get started. So we're going to take a look at Lab 7, which is, I told you it wasn't going to be easy, and I wasn't lying, with regards to how we generate, either those note structures or how we use those note structures to then generate sound. Because I guess for part 1, if you're still stuck on that, probably you have to come to my office hours today, especially if it's due tomorrow for you. I will do my best to help you get through it, but I think you have a lot of work ahead of you before your deadline here. For part 3, I think the challenge is primarily that it's another third-party library you're using. If it works, then you're fine. And if it doesn't work, it can be really hard to debug someone else's code. You really have to read someone else's code to be able to get your code to work. And it's also generating sound as well, right? If we're just generating a plot on a screen, you kind of know what a sine wave should look like, and you know if it's correct. Is it a sine wave or not? When you're generating a wave file, or using the player piano example in part 4, if it sounds good, you're fine. And if it doesn't sound good, I think it could be hard to figure out, okay, my thing sounds bad, and what does that mean? How do I get it to sound bad? Now, I said I wasn't prepared to jump into it, but what I can do is take one of you as tribute in terms of you'd have to feel comfortable with people in this class looking at your code. Couple volunteers. Dee Dee, is it? Can I open up yours? You're okay with that? No one's judging here. This is a judgment-free zone. Who's your lab partner, so we can share the blame with your lab partner as well? Okay, I'm going to open it up, and again, there's no judgment here. You can see very few submissions, right? People are still struggling with just this part 3 part. I'll say that if I look at this and if part 1 still isn't done, I may jump into somebody else's, but let's take a look at this. And let me just put myself in the mind of what I was hoping like the ideal lab student would be doing. I always want to have, and they're making it harder and harder to open up, I always want to have that README file open. Not just like the source code for the README, but the actual like nicely formatted markdown README file open. Every sentence I put in there, of course I have typos like anybody else, is intentional. I didn't just kind of randomly type some things. I wanted you to read through it. If I put some hints at the end, I wanted you to use those hints. You really do have to spend time, even when you're stuck with a bug, like looking back and saying, okay, what did the instructor actually expect you to do for this part? Because otherwise there isn't enough guidance if you're just trying to go into this starting code and do what you'd like to do with it. So in this one, the idea was that you were going to use your gen note struct array function from part 2, which the main challenge of gen note struct array was that we had this big, possibly multi-dimensional array of these note structs that you were creating. And some of the challenges I said, well, make it a global variable. How do you write a function that operates on a global variable? The closest connection we had to that in class is when we were doing that playing card example. And we had that global deck, which was really just an array of card types. Your code should look pretty similar to that for this part. I'm just going to take my first time looking through this today. I'm just going to take a quick look at your main. We have some headers. We have print note struct. We have gen note struct. You got your harmonics. I like this. This looks promising. Well, maybe this is already working though. So I'm going to play your wave file. It's not going to show up on the recording of this video because unless I maybe can really blast it or something. And I hear nothing at all. Is that your current outcome? You may have to blast it a little higher then. Let's see where my speakers are connected to. There may be some in-class. Oh, that sounds good to me. Now, I think it could be that to get it to show up in class here, I may have to like crank up like I don't know how loud this is, folks. Let's find out. Not loud at all. I will then at least play it on my own speakers here. Extron Scale D, Intel, that doesn't even sound like a thing. We'll try playing it on those speakers. Okay, so you can't hear it. Maybe it'll show up on the recording, maybe it wasn't. It depends on how you generated this code. So let me start at main then. Okay, main. Oh, your code looks fine. I don't know, this looks pretty good to me. Okay, we'll walk through it. You have an argc and an argv, but instead right now you're doing just scanf for the note and the octave. The instructions technically said, use argv we could write the code for that. But if you were finding yourself spending a lot of time on getting the argv code to work, then I'm fine with it. Just do scanf, just so you can get your code to test. So this was to play multiple notes. Right now, you're only playing one note. If you'd like to, we could, as a class, refactor that part to play multiple notes here. But right now, it's going to play a single note. You are then calling your individual gen note struct on that particular note that was input. This is probably straight from the example code for setting up that tiny wave library. And for the most part, you don't have to mess with it too much. Open up a file using a particular format. You're not supposed to mess with that. Write the actual buffer directly from that note using this call. Other people were saying, hey, or even as a specification here, copy things into this local buffer and then pass that to this function. But if you're just playing a single note, at least, in that single call, you can say, here's my buffer. It already exists. We talked a little bit. We have to talk more about it as a class, this equivalence between our pointers and our arrays. This is a function that is expecting a pointer to a buffer. We have this structure called note. In part of it, it has this array as part of the structure called buffer. We're passing that. We are basically passing the name of the array. That is a pointer to the first element in the array. We're passing it, saying that many samples we're copying over. We're copying over what works out to be 2 seconds of a note. You're finding something funny, though, other than it's all working, or am I missing some joke? Your code looks pretty good to me for this part. Now, a couple things that I would have suggested we do differently, and if I break it, I'll fix it later. I didn't want you for this part to use the singular gen note struct anymore. We have this nice function that generates all the notes, and I just wanted you to call that. That'll be at the beginning of all your programs. You call gen note struct array. Now I said it probably has to be global. This is one way to implement a global array, and I see part of the challenge you may be having is now you have this big array, and how do I go from a note and an octave to that big array here? So you have this big array of 108 notes, and you see that 108 defined there, and you have to write some code to go from C4 to which entry in the array that you have here. There's a couple different ways, I think that we can handle this. Just kind of thinking out loud here. This part is something that if you don't have in your code, the rest of you, this is probably going to be necessary. Some mapping of notes to index. It's not technically a map, but we can use it to build a map. There has to be a way to go from E flat to 0, 1, 2, 3, third offset in my octave. And I don't know of any better way to do it than just to define what my offsets are. Start with C, that's the 0th offset. That's just by the convention of how we were setting up the middle A note here. We could have done it otherwise in other ways. And then we have our definitions for an octave, which may not be as necessary here. And we have a function that's going to call our gen note struct, which takes in a note as a character, takes in an octave as an integer, and returns an entry of that note struct. And you did this as a static, which was one of our workarounds for how do we write a function that actually updates a whole bunch of stuff at a time. Static variables, which are essentially going to be implemented as a global variable just with a local namespace, a local scope of the variable name, is one way to do it. We could also, and one way you may want to consider refactoring this code, this is not wrong, you made it harder, I think, than it needed to be, is we can actually just go ahead and make this global. It's going to be unhappy, but we'll give it a second. And call it music notes. It's still a fine name for what you'd want to call that. And then this would be a function that is operating on a global variable for necessity that is in fact not going to return anything at all. The way you had it was fine. I think this is kind of what I had in mind when I said make it a global variable. It's defined outside of any function. It has global scope. Any function can now access those variables. So that when we call gen note struct array, well, that didn't work. Struct array, I don't think you have a prototype defined. That's all you have to call. And then afterwards, you may want to leave a comment like, now music notes has what we need or something. That's a pretty casual comment, but that's kind of what's happening there, right? We've called this function in main. This function is updating a global variable. We can now use music notes in main. It should have the values we would expect. It's got global scope. It's put somewhere else in memory. Anyone can access that variable. I called that a code smell last week, and I still stand by that. And in theory, this could be a stacked variable that gets returned or an array that's an input to the function. We haven't really covered how to do that really appropriately. It's a little bit of a hack for us, but it works pretty well for this example here. The other thing I'd like you to consider is, well, a header file would have been nice too. Let's see where we are here. I have to do a lot of scrolling. There should have been those like pound defines of the enumerated types, right? The different num notes, and those aren't defined anymore. Those are kind of gone. They've gone by the wayside. I think accessing, and that's okay. Accessing this array, it's 108 entries. That's still going to be the case. I think it'll be easier if you make it two-dimensional. Doesn't change the amount of memory it uses. It's just a different way of thinking about the dimensionality of the data. Or if you do 9 by 12 or 12 by 9, it's the same as having 108 elements. I think it just makes it a little bit easier that you don't have to keep doing this kind of linear arithmetic where you're trying to figure out which entry in that array do I actually want. Now let's take a look at this function. So for int, new octave equals 0, new octave less than 9, new octave plus plus. For note equals 0, note less than 12, note plus plus, one note plus plus. Car notes equals note name. That's your lookup to which character you actually need for it. I don't know. Call it notes, call it whatever you want. It's, note name or something. I don't know. That's fine. This array was called note name. Music notes of octave plus note. So the way you have it is you have octaves as that first dimension and notes as your second dimension. Again, 9 by 12 versus 12 by 9, it doesn't matter. That's just how you have it here. So instead we would do octave first dimension, note as the second dimension. That code should still work. We'll see. Now when I want to test whether we're actually still generating something that makes some sound, I'm no longer going to call gen note struct because I'm generating all the notes now, right? I've got every note here. Let's so instead of note.buffer, let's just grab one of the notes, and we get to choose which one we want for now. They're all defined as this global array. We got to grab one still, and it doesn't really matter which one we grab. If we want to do C4, that would be, octave would be 0, 1, 2, 3, and note would be 0, because that's our C note there. Copy that notes buffer. We still have to do this mapping in our code, but for now, no printf, no scanf. We're always playing C4. Took a little bit longer to run because that function to generate note struct array is actually doing a decent amount of work. It's copying a lot of data here. Seems kind of low. I guess I don't know what C4 should sound like necessarily. We can test, does C5 sound better? I don't know. Seems reasonable. That's kind of the problem with working with audio. So we don't have like a ground truth. You probably can find test note generators online or all sorts of ways to plug in a keyboard and confirm that that's roughly a C. Yeah. So we're off by one. Yeah, I haven't looked at this. So int octave is an array of size 9. And the value of octave, we don't actually need this. I don't think that variable is being used at all. I don't think it's being used. Which is fine. I don't think it's necessary because we do start at C0, I think. And we are just literally, there's no mapping necessary. We're starting at 0, going through 8, which I think is what we wanted. Again, somewhere I have to do a quick lookup of what C5 sounds like. Okay, C5 tone. Let's see. I'm sure we can find something for instrument tuning. I mean, it's probably not my strong suit here, confirming whether a tone is correct or not. Sounds off. But that's cheating. We can't just go up an octave and assume it sounds correct. Let's take a look at the code here. Octave of 4, 0, 1, 2, 3, 4. That's how we defined it, though. So, C5, though, is what I put in. So there's no offset needed. We would just literally type in 5 for octave of 5. Sounds great to my ears. Pretty good. There was a comment in there, which I don't know if you need to do it for this one or for the next one, which would be to kind of play around with harmonics a little bit, right? Which is to get your C5 to sound a little bit better, you can actually kind of average in, and this is a little bit of a simplification here, to get C5 to sound a little bit more natural, just a little bit, added a little bit of C6 and C7 and maybe C8 to it as well, and just kind of average all of those together. C5 will still dominate. It won't sound like C6, but it'll have a little bit more meat to it. Where I would want you to do that for implementing this kind of pseudocode for the harmonics would be all the way back in your gen note struct function. Because once you've called it, then it's done. And it looks like you may have it. Let's take a look. So num harmonics 3, but give me a second. That was like pseudocode, assuming the note was always at 440 hertz. So let me see what happens here. I should think about this a little bit. Okay. Maybe trying to kind of combine two things here. So let's go back to basics. Gen note struct, take C and 4 as an input, for example. It's defining that structure, sets the note name and octave. You have a function that I'm just going to trust that given a note name and octave returns the valid frequency, because that part is a little tricky, but if you got it done, that's wonderful. You would not generally want to define, okay, there's no harm. You define a local buffer. As you update it, you immediately kind of update the notes buffer as well. So unnecessary, you could probably just remove it entirely, like that buffer of I, because you're assigning it and then immediately using it, but no harm. You didn't hurt anybody in creating an extra kind of buffer here. That part looks spot on for me. Set the index to 0. That's for the MIDI example where we may have notes that are running for different lengths. You want to remember where you were in the notes. Now you have this code for the harmonics, and this is still kind of pseudocode though. This is assuming for A4, how would I set up 3 harmonics of A4? So this defined number harmonics, having an outer loop of K is still pretty kosher, but we need to do all of that. We need to do all that in that initial loop. So this loop, we're going to kind of comment out as like pseudocode, as like, here's what we'd like to do for this. Because if we go back to what happens in this code, the algorithm is correct. You're updating that local variable called buffer, actually this one up here, but you don't actually do anything with it. It doesn't become part of the note, so there's no harmonics in this. You calculated a harmonic, you stored it in a local array called buffer, you didn't do anything with it. It stays there, it gets deleted once you're done with this function. You want to take this functionality and put it right in here, in that preview. You want to kind of merge those two functions. So for each note in the buffer, T does not change. We can still, if we'd like, initialize, like we have it down there, buffer of I equals 0.0. Instead of then setting it, we're going to do an increment operation using that same exact for loop there. So for each harmonic, take it's new note.frequency times K times T times 2 times pi. And I do have to define that at some point here, the num harmonics. It doesn't really matter. I mean, it doesn't really matter where we put it. Just it's defined somewhere. This could also be like an input to this function if you wanted, like 1 is the default input for harmonics, and then you can play around with different options. Or we just change the pound define and recompile and rerun. This is kind of a hard-coded solution, but it's fine. All we did here is said, instead of just calculating the buffer of I as that frequency value, we're potentially multiplying the frequency by some constant integer. So C4, I multiply it by 2, I get C5. I multiply it by 3, I get C6. I multiply it by 4, I get C7. We add all those results together, and we actually then need to take that value, and if you just add the values together, you'll get kind of an overflow of like 1.0 will become like 4.0, and it'll sound very crackly. We just kind of want to wind up averaging all those values together. So take all those things we've added together, average them all. That's what we want to put in buffer of I. Let's copy temp.wave to right now we're playing around with what? C5. C5 1 harm dot wave. Let's run our code again. And let's now copy this temp.wave to C5, that'd be 3 harm.wave. And let's just see how they compare. It's not going to sound magical. Real music notes have a lot of imperfections to them, have things like attack and sustain and delay, and there's filters. Real music sounds a lot better than like kind of just pure sine waves, but it should sound better. Okay, that's the original. Sounds just lovely, doesn't it? Hopefully that comes on the video as well. Here is now with the 3 harmonics being added to it. Wouldn't say it's wonderful, but maybe it's a more solid sound compared to then going back to this piano C5. Your mileage may vary if that sounds better or not. It could be for the lower notes, it would sound a little bit better. So gen note struct array, the only change we made there is we're updating a global variable. And I just thought it was a little easier for me to think about this as not just one 108 element array. Just think about, well, we have octaves and we have notes. Treat each of those as a dimension. We just now have to say, how do we connect our notes to that entry in the array? Right now it is hard-coded, but now we go back to the quote-unquote true spec of the problem, which is I want you to do test out.wave where you play 1, 2, 3, 4, a reasonable number of notes. And those inputs, we talked about this a little bit, but we haven't had a ton of experience doing it. Those are what get passed to our main as that argc and argv. We get passed 2 variables that we can choose whether or not we're interested in via that mechanism of argc and argv. Argument count, argument vector, you can think of the other one as, it is a number of strings and then an array of strings that are what it gets passed. Literally what will get passed will be main, /main will get passed. Test out wave will get passed. C4, D4, et cetera, et cetera. Right now, it is hard-coded that output path. We'll want to write code to instead have it as a user input what we want that output path to be. So what I would put, if we just want to remember, if this was my example input, once we start messing with argc, argv, you want to have in mind what you want to do. In this example, argv of 0 would be what? Sure. Argc, I might have said it wrong. Argc is, you're fine, 1, 2, 3, 4, 5, 6, 7. Argc would actually be 7. 7 total arguments because we count the executable name itself. You always get an argc of 1 and an argv of 0 because the executable always has a name. It's called something. Sometimes we want to use that string because we want to print out application main had an error, and if you want to know the name of your application, that's where it's stored. And if you rename your application to something else, then it'll be called something else. But for a lot of our purposes, we can skip that first input argument, right? And say, okay, I don't care what my application is called. We're going to skip it. Argv of 1 is the output wave file. Argv2 through argc minus 1, whatever that winds up being, are the notes we want to play. Now, if you look at modern, like certainly command line applications, all these open source utilities we've been using in the shell all semester long, a big chunk of their code in main is dealing with this. argument process, parsing, determining whether you have valid input arguments or invalid input arguments so the applications themselves don't crash, so that they return a helpful error message. That winds up being in practice quite a bit of code that one would have to write if you really wanted to do this properly. I think unless the spec for our program we're working on says otherwise, we can assume, and I'll even leave a note, assume the input is correct. Like that somebody entered in something, or I think of another better phrasing for that, assume the input is valid. Assume that someone just didn't type in garbage at the command line. Because if they did, we could write code to check that oh, the second thing isn't a valid wave file, or the third thing isn't a valid note. We could check for all those things. We would just have to write 40 or 50 more lines of code to do that properly, and it wasn't the point of this lab, and so I don't think you need to spend time. Assume the input is valid. It is possible if someone sends invalid input that your code may crash. We could maybe do a very simple sanity checking that we know for this, we need to have at least 3 inputs for this program to be valid. argc has to be at least equal to 3 for this to be valid. We're guaranteed 1, we need a wave file, and we need at least 1 note for this to be valid. So for me, and this is pretty reasonable, I think, we can just check for that and get out of here so it doesn't crash on us. So if argc is less than 3, get out of here. And maybe print a helpful message. Error, or I don't know. Usage needs to be this, and test out.wave, C4, D4. The rest are all kind of optional arguments. Give some sort of warning message that, yeah, you didn't pass enough arguments to this. So when I hit the magic run button, and Replit does show this exit status 255 because, well, we return -1. If we want to return 7, okay, fine, 77. We can run it again. They're kind of arbitrary. -1 is a pretty standard way of saying something has gone wrong. But in this case, exit status 77, whatever. Non-zero exit status says that something probably went wrong, but it didn't crash. It actually returned the exact message that we told it to return, which is a reminder to you as the user of this program that you can't just hit the run button, you have to actually think about what the inputs are to this program. Okay, that's that. Return on line 161. On line 164, we can now, I think, assume that our inputs are kind of valid. So for our constant car output path, we can still use that variable, but we can still call it output path. But we know exactly what we want it to be. That's using the open bracket syntax. Let's use the pointer syntax. It's equivalent. It's going to be argv of 1. Now, when we pass it that wave file somewhere, it'll open a file by that particular name. We've talked a little bit about different ways you can get your input arguments. You can specify it here in the replit.replit file, which is every time I hit that run button, here's what gets executed. I kind of prefer doing it on the shell kind of manually. So now I'm no longer pressing that button. I'm going to just be manually hitting make. And now I'm going to be manually hitting running main. Didn't pass it any input arguments. It's pretty unhappy. Instead, I do my new wave.wave. Doesn't know anything about notes yet. We haven't checked for that. And we need to pass it a third, but it doesn't really matter what the third input is because we're not using it yet. So some garbage is our third input. That should have generated my new wave.wave. It does show up here. And it's the same note as before because there's no code yet that checks that third input to see what notes that you actually want. Opened up the file based on argv of 1. Now we have this code that is calling this function, and it turns out, although it's not, I don't think it's inherently obvious that, based on the spec, you have to look at a little bit of the documentation. You can choose to call this function as many times as you want. And you can then, just to explore with it, although I haven't explored with this, that's my C5. Let's also pass C6. Let's do both. And it'll be the full 2 seconds, but that's what we specified here we wanted to do. Again, I'm going to manually do make. If you get sick of like typing things, just type make, put a semicolon, put the /main, and then whatever you want to call it next. And then you just press up to kind of recall the last thing that you typed in. So now it's just as easy as pressing the run button. It's compiling, taking its sweet time. It's now, it'd be good to check that that file was new. Like, did I actually update that file? We could always exit, we could always run it. The other command that's useful is ls to list my directory contents, -l for like the long listing. That shows you the timestamp on the files in your directory. That is sometimes helpful. It's today, October 30th. Oh, tomorrow's Halloween. Any costumes that you're going in? No? No, nothing? I'm disappointed. It's awfully cold. Tonight is trick-or-treating then in Des Moines, and I think I'm just gonna go huddled up in winter gear, and that'll be my costume. Cold dad who's kind of over it all, but still feels obligated to walk around for a couple of hours. Okay. I don't know about the timestamp. Maybe that's not as useful as I thought it would be. It definitely lets me know the file was created today. That timestamp, 37 minutes after the hour sounds right, but then that says 5:37, so there might just be some time zone difference. So it's not as helpful as I thought. 5:37 in the afternoon would be 7 hours ahead of us. So maybe this server is located in the UK. I don't know. I'm not sure why it gives me that timestamp, but let's check this file. Again, what did we change? We called that function twice. Give me C5, do it again, and give me C6. This should be a 4-second file. Well, that's a good sign. It is 4 seconds long, and it should be the note followed by another note. Yeah, it sounds lovely, we know. Okay. To my untrained ear, that seems reasonable. So we now know we can call this function basically as many times as we need to. How many times do we need to call this function in terms of variables that are already defined in this program? A number of times. Equal to argc -2. Okay, I think you've got it. I want to make sure people are on the same page with regards to this. When my input was this, how many notes should I be playing? 5. What is argc in that case? 7. So the number of times we need to loop through this is going to be argc -2. Because argc includes both the /main, which is kind of irrelevant, and it includes test.wave, which we used, but we're not using anymore. So to me, we want a for loop for this. And it shouldn't necessarily start at 0. It should start at 2. This code isn't going to work as yet. I mean, this would do something, but it would be playing the same 2 notes over and over again. But that's how many notes we know we want to play. And now we just kind of got to grab them. We have a string. So for now, if we were curious, we could say, we could print out argv just to confirm that our inputs are what we expect them to be. Now I can't put that, I have to put something valid in here. C4, C5, C6. We run it, it prints out C4, C5, C6. We have a string that has C4, we have another string that says C5, and yet a third string that has C6. There are functions that allow us to go from an arbitrary string to a set of variables we may be interested in. You are very welcome to use those functions. We haven't played around with a lot of them, but while we're pretty good with scanf at this point, the function that we would use would just be called scanf. Take a string and treat it as a user input, convert it to a char, convert it to an int. That is totally valid for this problem. Scanf, I'll just say, is perfectly valid for this problem. But this problem is actually a little simpler than that because it's always note followed by octave. So for me, I just want to grab those 2 things. Char, we should have called them name, note, name, or something. I'm going to call it now that I have the time. Argv of I of 0, that first character, right? And I have my octave. How do I grab the octave from that? So it's C4. C is that string, that's of I. The first element in that string, that's offset 0. How do I grab the octave then? It's very similar. C is the first one. Say it again. You have to say it again. So argv of 0 would be the /main. This would be the ith character in /main, so not quite. We still want argv of I, because that's C4. That's the one we're currently on, and then it'll be C5, then C6. But what do we want in argv of I now? Not offset 0, but offset what? We want the next one. That is a character. We technically want the integer equivalent. So if it's character 4, we want to return the number 4. There's a lot of different ways you can do that. You could always just subtract like the character 0 from it, and that'll give me the offset from character 0. That only works with single integers of the range 0 to 9. If you have more complicated character string to integer conversion, you want to use scanf, but it wasn't necessary for this purpose. So we have a note name, which is C. We have the octave, which is 4 or 5 or 6 as an integer. We're not quite done. We're getting pretty close, but there's one more step of what we have to do. And what is it? I couldn't hear. We can try it. I think we're going to find it's going to be not as fun as we would hope. It's not 5 of 0, but it's definitely octave, but not octave of note name. That will do something. That will probably crash. We can try it. Let's crash it. We never get to crash things in this class. Yeah, okay, that crashed. And you throw your hands up in the air, and what does your instructor tell you that when you get a segmentation fault, what happened? Pointer, you access something out of range. Oftentimes it's an uninitialized pointer, but that's not the case here. Octave of 5 or 6, that works. When we wanted C, what did we pass to that? Offset 0. We didn't pass it the letter C. What is the letters capital C? And you can probably look it up quicker than me. It's like 45 hex or something, right? It's a really high number. This is then accessing this two-dimensional array, offset 5, offset 45 or whatever. There isn't that many offsets. It's out of range. It's going well beyond the end of that array. Even though it looks correct, we calculated a note name, we got our octave, but this is not accessed via a character. How do we access that? Via that offset. How do we go from the letter C to the value 0 then? You have to speak up again, sir. This code's helping you. You're allowed to contribute here, okay. You know, it would be lovely if that worked. Because I wish notes worked that way. This problem would have been a lot easier. Doesn't quite work because the notes don't go in alphabetical order, and then there's lowercase notes and things like that as well. Yeah, so you don't. So for that kind of manipulation, I like the thought process, and I did kind of follow it. So subtract C, you don't have to convert it to int first. Characters are just small ints. Yeah, but it's not going to quite work. It'll work for C, actually. Okay, it'll work for C. So let's do it for C. It will work for C. So I take that back. Probably get rid of this, printf of thing. What did we call my new wave? That wave, fine. That's not what we really wanted to call it. That should be 3 notes. It's sounding pretty high to my ears, so it's not sounding super lovely. It's going to get even higher. Okay. It worked for C, so you move on, you're done with your code, and then you look at it later and it doesn't quite work. Because this code is basically going to happen again in the next part and the part after that as well, which is how do I go from an input to the note I want to grab from that array and writing it to the wave file at the end of the day. So the same exact logic is going to work. That worked for C. Let me think of a note that it would work very poorly on. Yeah, which is lowercase c, right? Was that even an option? B flat, thank you. Not a musician. Okay. All right, I don't know what this is going to do. Let's find out. doesn't sound like half a step down, right? A one step down. That logic is a nice shortcut, but what do we know? And I don't think you are still using it, so I'm just going to copy paste it, but then comment it out. We have this, right? We have this mapping of note as a character name to offsets into an array. You should have done something very similar in your logic before, but now you're doing the exact opposite step. So where did we use that array? Or did we? I hear other people playing notes. That's good. That's a good sign. Here, we do the exact opposite. Give me the integer offset, and it generates which character you have. Now, better programming languages than C have this concept of a map as a data structure. So you give it an input of C, and it returns 0. You give it lowercase d, and it returns 1. We don't have that as a built-in character, but we can do the same kind of functionality here. That when we have note name of C, we still have to figure out, call it note offset or something like that. We have to calculate that. We have to figure out what our note offset needs to be before we write anything to that wave file. Convert C to 0, D 1, etc. How do we do that? Take a moment. Turn to your partner. I'm not going to do it for you. How do we write that code? Take a minute. Wake them up if need be. Everyone has to have something pretty similar to this in their programs to get this to work, because you're doing that conversion for 3, 4, and for 5, but it should be basically the same. Take a moment. I only gave 2 examples there. I mean, there's more, right? So it's all of them in order. D is 2, E is 3. That's how we set it up. That's the right way, I think, to set it up. How do we actually do that, given that note name array? And again, assuming that nobody's entering Z or Q or something like that. That was kind of our simplifying assumption up here, that assume that otherwise the input is valid, just to make things work for us. But we could write that too if we needed to. Let's just take another 20 seconds here. Thoughts from somebody I haven't heard from yet today? How do we do that? Oh, yeah, sure. I guess that counts.
Find the position of that character in our node array.
Find the position. I'm going to write that down. Now, and let me just say that I think for some of us at this point in the semester, that's a sufficient answer, right? Okay, and you know exactly how to do that. That is a correct statement. Let's find the position of that character in the note array. Where I need you to get to relatively soon, collectively as a class, is understanding that that's most of the answer, and the rest is just syntax. We need to find the position of that character in the note array. We have an array, it's called note name. Oh, I shouldn't have called it that, though. My note name, I don't know, fine. And we're going to eventually use note offset here. Note index is probably a better name than note offset. So my note name is the C, or the D, little d, or the big D, or the little e. We need to then convert that to an index, 0, 1, 2, 3, 4. I don't think there's any clever way to do it other than to, at some point, have hard-coded where each node is relative to each other. There isn't, at least to my knowledge, especially because there's not an exact pattern to it. It's not in alphabetical order. It's not an exact matching of lowercase to uppercase. Just having it coded in your program as here's my array of characters and where they are relative to each other, I think is probably just still the best way to do this. But we have that array. It's called note name. To find the position of the character in the note array, maybe we want to call it like note name array, you can write a for loop. We know exactly how many times to iterate. Let's use note index because that'll be fine. Note index is less than what? We're going to iterate through that array. So we start at 0. Where do we stop? Which is how many? We usually say, the way the math works out for these arrays, there's 12 in here. So the valid indices are 0 through 11 inclusive. So we can always usually just write that using that length information. Other people, I think we're supposed to call that num notes or something like that, but 12, it's hard-coded in this program, it'll work. That'll give us valid note indices of 0 through 11 inclusive, note index plus plus. How do we know if we found it in the array? We have 1 more minute to make beautiful music here. How would we know? We have my note name. Find the position of that character. Not very well phrased. My note name character in the note name array. How do we know if we found it, if we've matched? How do we check if 2 things are equal? Hash table? No. If statement. No, okay. I was thinking, boy, hash table would be awesome. It's doable, but that's okay. If statement, right? If the things are equal to each other, we found it. If my note name, capital C or lowercase d or whatever we have, is equal to what? No, that's like hard-coded. We want to check for this array. Have we matched it? The nice thing about this if statement, and we'll still put the braces here, if it is matched, we don't have to print out, hey, you found a matched. We actually have, we've done it, we're done. They matched, it matched at 0, and we assume there is a match, that we didn't type in Z or Q or something like that. We eventually matched in that array. Note index will be the value we want. We just get out of that loop entirely. It was the 3rd one, it was the 4th one, it was the 5th one. I do not recall if these note sequences are especially pleasing or not, but let's run our code with this as our input from the README. Now it's test.out.wave. That ran awfully quick. 10 seconds, 5 notes, so quick sanity check. It's at least doing something reasonably close to correct. And now we can all dance. Doesn't sound that great, in fact. Just going up from C to F. I think those are the speakers that sound bad. Okay. For now, for part 4, which we can't do right now, it's a different input format. It's a format that allows you to do slightly more clever things than playing 2-second notes at a time. The main difference will be in this call, and the rest is going to be very similar. It's just parsing input again for part 4. For part 5, it's also parsing input. The input's a little bit more abstract. You're still just calling tiny wave write with different notes in my big note array, depending on which notes you need at any given time. Leave things here for today. I expect to hear beautiful music in lab this week as you get it all done and show off. Okay, good luck.